From toxin to disease detection, molecular sensing has proven to be an integral part in various modern sciences. However, to this day, these techniques struggle with optimizing the method of detection as it faces various issues related to the structure of the sensors as well as the associated limit of sensitivity. Hello, I'm Sarayan, and I'll be presenting an overview of our study titled Optimum Grating Parameter for Diffractive Label-Free Biosensing under the Photonics Research Group of the National Institute of Physics, UP Diliman. So what are biosensors? Biosensors are instruments which combine biological and physiochemical components to produce a signal to detect target molecules. For optical biosensors, they integrate optical elements to act as transducers of the system to convert the molecular events into understandable signals. One technique of optical biosensing, known as diffraction-based sensing, aka DBS, incorporates a functionalized diffraction grating composed of probes or capture molecules to capture analytes. These analytes produce a change in the signal which can be measured using the diffraction efficiency. By analyzing these changes in the diffraction efficiency, DBS can determine the presence and concentration of these analytes. One way to analyze diffractive optical elements such as diffraction gratings is by using scalar diffraction theory. Scalar diffraction theory gives accurate results when the period of the grating is much larger than the wavelength of the incident light. Furthermore, it ignores the polarized nature of light. From it is possible to determine the effect and optimal conditions of each key grating parameter. In our study, analyte adhesion was modeled as a thin film layer on the grating surface. And in doing so, it was possible to determine a new analytical expression for the diffraction efficiency that considers the phase contribution of analytes. From this equation, it was possible to determine the optimal fill factor, groove height, and phase difference of the grating for maximal sensitivity. In addition, both a rough grating and a misaligned grating were simulated, as in practicality, the fabrication of these gratings are never perfect. By observing the average diffraction efficiencies of these perfect gratings, it was possible to determine how they prevent diffraction efficiency from detecting analytes. That concludes my presentation. Thank you for listening, and thank you for your time.